All right, hello everyone. Okay, so let's say we want to do some cryptography. What do we need? Well, at the simplest level, what we need is we need an encryption function and a decryption function. The encryption function obviously goes from some message space, the messages that we want to send, to some ciphertext space, which is the encrypted version of the message. And the decryption function goes the other way, and they're mutual inverses of each other. Now, if you define a cryptographic protocol with only one encryption function and one decryption function, that's certainly not very good, because if someone intercepts your message, then they can just try the only available decryption function and decrypt the message. And so what you actually need is you need a whole collection of these encryption and decryption functions, preferably indexed by some parameter, which we'll call f. And the whole point here is that this parameter is what's known as a shared secret, meaning two parties that want to communicate with each other, they have some mechanism of establishing what this parameter is, which in turn determines what encryption and decryption functions they're going to use. And then once they know this parameter, they can, encrypt and decrypt messages at their leisure. And so a big challenge becomes, well, how do you establish this shared secret? How do you choose this parameter? In the past, you can sort of imagine that maybe people would have to meet privately and decide, on the parameter and, meet together and say, well, okay, s equals 3, and then maybe s equals 3. But in the 1970s, two people named Diffie and Hellman actually showed that there's a way to agree on S over an open channel. And what that means is that if we have some open channel, let's say the internet, which you sort of always assume somebody is intercepting your communication, or you're just yelling across a room or whatever, there's a way of agreeing on S so that people who are listening in the middle don't actually know what S is. Okay? And so how did they do that? Well, what they said is, okay, suppose we pick a group G, capital G, and we fix a little element, little g, in G. Then the two people who want to communicate with each other, let's call them Alice and Bob, they can each pick an exponentiation map. So what happened here is that Alice has picked an integer a, and the integer a defines an exponentiation map, which sends x to the a. Similarly, Bob has picked an integer b, and they both compute their exponentiation map on this element little g, and that gives them g to the a and g to the b. They then send the results of their computation over the public channel, and then they apply their exponentiation map to each other's results. And because these two maps commute with each other, they both end up with g to the a, g to the a to the b, which is the same as g to the b to the a, and they can take this value to be their shared secret. And the key point here is that in certain groups, this problem of determining g to the ab from the public information, which is sent over the public channel and also consists of the group capital G and the whole protocol, it's hard to determine what this g to the a value, g to the ab value is. Now, this doesn't work for all groups. So obviously, if we pick something silly like the multiplicative group of the reals, for instance, you could just compute a logarithm. You could compute log base g of g to the ab and compute the value of a, and then, if you can compute logarithms, then you can certainly break this. But in many groups, this logarithm problem, commonly called the discrete logarithm problem, is hard, and so that gives us good confidence that this problem is also hard, and in those cases, you can do this protocol. Okay? And so this works very well. It underlies a lot of cryptography that's done over open channels. There's also similar, if you look at RSA, which isn't quite based on this, but sort of uses related techniques and also uses similar exponentiation maps. It's also, you can communicate entirely over a public channel. And so this works very well. It's a very nice paradigm, and it's under attack. It's under attack. In particular, the people in the fancy building next door are attacking it. I don't know why. They're building this thing called a quantum computer, and the basic idea of a quantum computer is that you can, ruin cryptography on some level. And the way that happens is that if you look at these problems, so this is basically what I just said, is that all these crypto systems that work entirely over an open channel are broken by quantum computers. And the way they do that is that they can break these two hard problems that sort of underlie these crypto systems, the discrete logarithm problem, which I just mentioned, and also they can factor integers, which breaks RSA. And the way they do this is that quantum computers are very good at certain kinds of algorithms that exploit this group structure that is sort of underlying this protocol. So that in particular, they can solve this very general problem called the abelian hidden subgroup problem. It's not really important what this is. I just sort of put it on this slide for completeness. But basically, if you have a group G and you have a subgroup H of G and you want to find a generating set for H, then a quantum computer can do that by sort of exploiting some function whose action is defined on the cosets of H. It's not really important, but the point is that this group structure, which we used in order to get these exponentiation maps to the Diffie-Hellman protocol, it can sort of undermine everything we're doing and cause cause the whole thing not to work. So if we look at this diagram again, we can ask ourselves, well, why did we need this group? What does the group do for us? The group basically does two things for us. First of all, it gives us a space of these possible S values, these possible shared secrets. And it also gives us a way of choosing these exponentiation maps, which commute with each other. Okay? If you look at it, no other group properties are really used. I mean, nowhere on this slide does this slide use the fact that, say, every group element has an inverse, or that there's an identity element of the group, for instance. Basically, the only thing that's required here is that you have two maps which commute with each other, and some space of things that you can act on the maps with and get some result, which is then your shared secret. And so what we'd really like to do is we'd like to write exactly this diagram. We'd like to draw exactly this diagram, but just with different notation and a different context where there isn't this group underlying everything. And so that you can't just exploit the group structure and break this protocol. But we really want to just draw the same picture with different notation, and then we can save cryptography in some sense. Okay, so here's the same picture with different notation. I've replaced the word group with something called a supersingular isogeny class, whatever that means. These exponentiation maps have been replaced with some kind of quotient. All the symbols, the x, g, and g to its various powers have been replaced with e and various quotients of e. But it's not really important right now what these symbols mean. I will try to explain that. But the point I want to emphasize is that this diagram is basically the same thing as this diagram under a change of notation. The only thing that's different about this diagram is this asterisk here that tells us that this diagram is not actually accurate. But other than that, this is basically the same diagram. And so let's talk about elliptic curves. So what is an elliptic curve? Well, simply, in sort of a simple way, an elliptic curve is just the set of solutions over some field to an equation of this form. If you look at this equation closely, it may occur to you that I may have forgotten how to count. There are 5 coefficients here, numbered 1 through 6. This is actually not my fault. This is a convention. You can actually see this in elliptic curve books. There is a reason for this. But in any case, the equation is usually not written in this way. It's usually written in various other ways. And the reason for that is that when we talk about elliptic curves, what we're really interested in is sort of the relationships between the points on the curve. And certainly if you're interested in the relationships between the points on the curve, you don't actually care about where the x-axis is or where the y-axis is. And so just like you can shift a parabola, you can shift the y-axis in a quadratic equation to get rid of the linear term, and you can shift the x-axis to get rid of the constant term. You can shift the x and y axes in this way in order to get various different forms and also do some other transformations. And so commonly you'll actually see elliptic curves written in a form that looks something like this. The Weierstrass form at the top is very, very common. The Montgomery form is useful for certain kinds of calculations. The Legendre form has certain theoretical properties. These forms don't always exist for various reasons, but the point is that there's many different ways of representing these curves, but they're all really equivalent under some sort of transformations that you can do. Now, one of the really, and there's also a technical condition, which is that elliptic curves require that there's a unique tangent line to every point in the curve. That will become important later. So here's some pictures. It's important that you sort of see an elliptic curve, and so it's not just an equation. So basically what's happening here is that we're varying the values of A and B for this Weierstrass equation. And this one here is invalid because it has this cusp here, and there's no unique tangent line at that point. I don't know how well these diagrams come out, but hopefully you can see that. Now, hopefully this is the right side. Okay, so the really interesting thing about elliptic curves is that they have this associated group. Now, normally when you have a group in mathematics, groups come from sort of obviously group theoretic things. Like you might have some symmetries of some object, or you might have some algebraic structure, and you sort of restrict to looking at some aspect of that algebraic structure, like the group of units of a ring, for instance. And those are sort of things that are very obviously groups. The elliptic curve group is something that is very not obviously a group. And so what exactly is it? Well, when we define a group, we need two things. We need a set and an operation. So here's a perfectly serviceable set. I will amend this shortly, but for now, let's just take a set to be the set of points on the curve. And how are we going to define our operation? Well, we need somehow a way of taking 2 points on the curve. There are 2 points on the curve and getting a third point. And so what we're going to do is we're going to draw a line. the line is hopefully going to intersect the curve at a third point. And these curves, it turns out that they all have this sort of symmetry about some horizontal axis, so we can reflect that point down here and call that point A plus B. It's a very odd thing to do. It might occur to you at first that it's not even clear that this operation is actually well defined. I mean, it might not be true that if you take 2 points on the curve and you draw a line through them, you actually intersect the curve in a third point. In fact, that isn't true. So, for example, if you draw a vertical line, the vertical line certainly doesn't intersect the curve at a third point, and so it seems that our group operation fails very quickly. But what we can actually do is we can add an additional point to our curve, and we're going to call this point the point at infinity. And we're going to say that all the vertical lines intersect this additional point at infinity, and we're going to say that when you take these 2 points that are intersected by a horizontal line, that A plus B equals infinity. And we're also going to take the point at infinity to be our identity element. And so this way we get not only an identity element, but also inverses. Because if you have an equation of this form, it just tells you that B is the additive inverse of A. So, I mean, okay, this kind of works. It seems somewhat non-intuitive at first, yeah?
And when A equals B?
Very next point. Okay, so when A is, you want to add A to itself, this is why I said before that you need a unique tangent line. Okay, because when you need a unique tangent line, I mean, you can't draw a secant line through a point in itself, but a tangent line is sort of a limit of secant lines, and so that's why you have a unique tangent line, which then gets you your point, which you then reflect as before. Okay, so that was, I in fact prepared this. And so this in fact does get you some operation, and it is, there are inverses and there is an identity element. But here's the question: why is this associative? Why would it be true that if you take 3 points and you first add A plus B and then you add C, it's the same thing as taking A and then adding B plus C to it? Well, I mean, we can try. So here's 3 points. Here's the line. There's A plus B. Here's another line, and we flip it over, and then there's A plus B plus C. The other way we do that is we first add B and C, so we draw that line and get a point up here, flip it down there, draw a line, and it intersects the exact same point, and we flip it back and get A plus B plus C. There are good explanations for this that involve some complicated algebraic geometry and so on, but this just works. It turns out that this works, and is it?
2 cubics that intersect in 8 points. Sorry, if 2 cubics intersect in 9 points, and the third cubic intersects 8 of those 9 points, and the third cubic must intersect at 9 points.
Is that a simple reason?
Yes.
Okay.
Here the cubics are various subproducts of the lines.
All right, so there's a simple reason for this. So I didn't promise just elliptic curves. I promised these things called supersingular elliptic curves. The basic thing is that a supersingular elliptic curve is just a very special type of elliptic curve. There's many different characterizations of this. One is in terms of something called the endomorphism ring of an elliptic curve. So I mean, in mathematics, and you have objects, you always talk about sort of morphisms between the objects and other objects. And since there's a group operation here, you can define a ring that you get from, sort of multiplying the two things by function composition and adding using the group operation. And so the supersingular elliptic curves are just the ones where the endomorphism ring is sort of really big. It's isomorphic to some, order in a quaternion algebra, if that means anything to anyone. And the normal elliptic curves just have very simple endomorphism rings. So in some ways, a supersingular elliptic curve is just an elliptic curve that is sort of very special and has a lot of structure. There are some other characterizations in terms of the group of p torsion points. There are some characterization where if you write an elliptic curve in Legendre form, the supersingular elliptic curve is the one for which the lambda parameter is the root of this polynomial. There's some other characterization where, if you write the cubic that defines the supersingular elliptic curve in the projective plane, and you take the p plus first power of the cubic, then the xyz term will be 0 if and only if it's supersingular. You can look online and there's 20 different characterizations. The point is just these curves are very special, and we need to choose these curves so that our corresponding hard problem is hard. Otherwise, the things more or less work the same way. The other thing we need is some notion of quotient. Typically in mathematics, a quotient is associated with some kind of surjective map. And so the same thing is true here. Our surjective maps are called isogenies. This is why the term isogeny enters into the name of the protocol, and why before it was there was something I called a supersingular isogeny class. An isogeny is basically just a non-constant rational function which fixes the identity point on the curve. There's some details with this definition. There's typically these things are defined in terms of algebraic geometry, and it's difficult to define them quite properly, but this is approximately what it is. And it's actually a theorem that such a map is always a group homomorphism. So you just get, it just ends up being a group homomorphism and preserves the group operation. And they're also sort of associated to the subgroups of the elliptic curve group. That sort of makes sense, because if you want to have an elliptic curve and you want to quotient by something, the something will be sort of a subgroup of the elliptic curve group. And so if you provide a subgroup of the elliptic curve group, then there's these formulas called Bailey's formulas, which will give you a unique isogeny, unique in the sense that it gives you a corresponding image curve, which is sort of unique up to isomorphism with that particular kernel of the elliptic curve group. The point here is that we somehow have a way of creating these quotient curves. Okay, and these isogenies let us do it. And so the image curve under the isogeny is what we call the quotient curve. Okay, so if we look at this diagram again, what have we found? Well, these maps here are these isogenies. These elements here are all supersingular elliptic curves. And that's basically it. These particular things that we're quotienting by are subgroups of the elliptic curve group that are generated by a single point that are each are chosen by Alice and Bob. The only thing that's left to explain is why there's this asterisk here. Okay, so why is there the asterisk there? The asterisk is there because of the following problem. Okay, suppose that Alice receives this curve, E quotient R to B from Bob, and she wants to compute E quotient R to B quotient R, the group generated by RA. Well, the problem is that the group generated by RA is really a subgroup of the elliptic curve group of the original curve. It's not a subgroup of the elliptic curve group of the quotient curve. And so what Alice really needs is she needs something like the evaluation of Bob's isogeny on the group that she's chosen. But the problem is that if you get Bob to evaluate the isogeny on the group that she's chosen, and you send that over the public channel, that will compromise the security of the protocol. And so you have come up with a different way, a very special way of choosing these subgroups that you're quotienting by. The way you do it is you choose special points, PA and QA on the elliptic curve, which sort of generate the right sort of subgroup. And then Alice picks some integers, and she computes a linear combination of these 2 points. And then after she's computed a linear combination of these 2 points, she gets Bob to evaluate his isogeny on these particular points. And because the isogeny is a group homomorphism, this sort of distributes through you can pull the isogeny out and get what you want, which is the isogeny sort of evaluated on this point, and then Alice knows what the right subgroup is that she has to quotient by. There's a reason why I put this sort of at the end, with sort of the technical detail. The intuition is this picture, the picture that I can't back up to right now. That's basically what happens. So there is some technical issues in making this diagram exactly work, but the intuition is the diagram. The last thing I want to talk about is what I've been doing, which is sort of appropriately condensed in one small slide at the end. There's 2 bullet points, but I think the paragraph's big. But basically, so there was an implementation of this protocol developed by Microsoft, which is sort of the leading implementation. And all this computation is done over finite fields, very, relatively large finite fields with numbers of around 768 bits in size. And when you do this kind of computation over finite fields and you want it to be efficient, you have to use special assembly language instructions for the particular processors that you're using. And they did this for x86 platforms, but they didn't do it for ARM. They just had a generic implementation for ARM. And so I wrote a lot of hand-coded 64-bit ARM assembly, and I optimized all these finite field routines, and I was able to improve the performance by about a factor of 10, which I was happy with. The other thing is that when you transmit these cryptographic keys over the public channel, in most sort of post-quantum crypto systems, the keys are quite large. But in this particular scheme, and especially if you apply some compression techniques, the keys are sort of a comparable size with the existing protocols. And so what I've also been working on is implementing these sort of key compression techniques, which make sure that the keys are sort of reasonably sized and comparable with the cryptography that currently exists but is vulnerable to quantum computers. So that's everything. Thank you very much for listening.